with slope fields. Are you guys good with creating slope fields from order pairs, or?
No.
All right, so these are basically derivative. Differential equation is basically a derivative formula, and this can help us get any information about slopes, and as long as I give it an order pair. So we can start off with an order pair at -1, 2. Right, so I'm just starting off at one point here. So let's insert -1, 2 into the derivative equation. And what do we get? Okay, what's that going to be equal to?
-12.
Yep. And -12 is a really steep slope in the negative direction. So we're just going to make our best approximation that we can. Through this point, we'll represent slope of -12 to the best of our abilities. Okay. And we repeat the process for each of these order pairs. So this is -1, 1. Put into our slope formula. And what do we get there?
-4.
-4. So -4 is still negative slope, but not as steep. So we'll just try to make our best guess here. Not as steep as this line, but still relatively steep. Right. Accuracy is not too important, just as long as you're able to represent a fairly, as long as you're in a ballpark value, that's good enough. Or in terms of ballpark notation, that's good enough. Okay, so we just repeat the process for all these order pairs. Right, -1 times -1, that's a +1. So if I get a +1, I want to change my orientation now to be rising from left to right. So maybe it's not as steep as that. Okay. So it's just kind of busy work, right? Just plugging, taking order pairs, putting into the slope formula, getting a number in return, and creating that slope. So the idea is that right now these are only a few points, but if we were to create and generate across a larger region, then we can kind of have an idea how the original graph is going to look. At least what is in terms of the solution of this graph, in terms of how the flow of the graph is going to look.
Yes.
So something to point out though is I know we're not going to get it in these order pairs, but let's say the order pair produced a slope 0. So what would it look like if I were to put a slope 0 through an indicated point?
A straight line?
Yeah, horizontal line. And let's say I evaluated slope and I got something that's undefined. Let's say I got like 9/0. Hey, do you know what we do for that point?
You just leave the point as is?
Yeah, leave it empty. Yeah, I think a lot of students may think of it as, well, what about vertical line? Isn't the vertical line undefined? Yes, but not for slope fields. For slope fields, it'll just be undefined, meaning that there's nothing that's going to come out of it. So you'll leave it blank. Okay. Lutzoff, you okay?
Yes, sir.
Yeah, I'm good.
Okay. All right, so it says find the particular solution. Now we're moving into the meat of this unit, which is solving differential equations, which means we have to separate the variables, take the antiderivative. Once the derivative notation is gone, we have to solve for y, we have to solve for c. So quite a lot involved with this problem. So let's start off. I'll do this work on a separate sheet here. And by the way, this is a worksheet 4, morning review, which is under yesterday's link. Okay, it says find the particular solution given the differential equation, or slope formula, with the initial condition of f of 0 equals 1. Okay, so part B. And what I like to do is I like to begin thinking in terms of cross product, because my first goal is I want my dy and dx in their right places. I may not get full separation of variables, but I will get my dy and dx's off to the right location, the right spots, and then we can worry about if anything else that needs to be moved. So I'm just putting a 1 under the denominator here just to kind of help me understand how I'm going to cross multiply here. So cross multiply here, 1 dy equal to okay, good so far?
Yes.
So the nice thing is, okay, we know those are set. Those aren't going anywhere. Those are where they're supposed to be. We just have to decide, does anything else need to be moved? Okay, what do you guys think?
The 2y minus 1.
Yeah. We don't want to expand this out. The parentheses are there to help separate these expressions for us. So we'll leave them separate, but we know we have to move the y because we want the y's together, but because the 2 and the 1 is stuck inside the parentheses with it, all that's going to come along with it as well. So we'll divide the 2y minus 1 over to the left side. All right, so let's clean this up and see if we can move forward. All right, what do you guys think? Full separation of variables? Okay. X is together, Y is together, we're good, right? Okay. So now we got to decide what integral rule can I apply to take this derivative notation and move it up a level to the equation function level. Okay, I think the right side is pretty easy. These are both power rule terms, but the left side, what do we need to involve on the left side? Any ideas, any thoughts?
Natural log?
Yeah, that is we know that we're working towards this rule, right? But to get there, though, we first have to understand that this is too complex for even this rule to handle. So we got to go through U-Substitution, right? Oh, sorry, not this one here. But it's nice to kind of have some indication as to what rule that we're kind of what rule we're trying to aim for. So if we go to U-Substitution, what's our U value?
2y minus 1.
Yeah, that entire denominator will ensure that we can get that hopefully to to resolve itself. So okay, our u value is 2y minus 1. Okay, we find the derivative, du over dy. Okay, Utsal, can you try this here? What's the derivative of 2y minus 1? Any ideas off? Okay, so just do power rule, right? So 2y minus 1 just becomes 2, and negative 1 goes to 0. So just 2. Okay. Cross multiply, solve for dy. And then we just want to isolate dy by itself. Okay. We make our substitutions. Push the 1/2 out in front. And we should be at the same level now. So we did all this work here to get it ready, but we know now we can apply our antiderivative rule, and then the right side also has its own set of rules that we can apply. Okay, left side, integral of 1 over u, natural log of u. And the right side, we just do power rule. And then we can do a little bit of cleanup or replacing the u back in terms of x. Or sorry, in terms of y, sorry. All right, how are we coming along here? Bailey, Utsov, are you okay?
Yes. I don't think his mic is working.
Oh, really? Utsov, are you having trouble with your mic? No, I can't. Oh, okay. Do you want to try restarting, coming back in, or you just want to just listen in? Okay. Okay, then Bailey, you're good here?
Yes.
Okay. So we've kind of gotten it down to a general equation. We still got some cleanup to do. We still got the order pair to work in, but you know, our calculus portion is done. So I'm always looking at the left side and just asking myself, okay, even if it's a small thing, is there something small that I can take care of? And I always want to try to leave the left side kind of as minimal as possible or as cleaned up as possible. I'm going to go ahead and move that 1/2 over to the right side. It's a small thing, but it'll just make my process easier. So multiply everything through by 2. 2 over 4 is just 1/2. Minus 6x plus 2c. Now 2 times c is just a constant, so we're just going to leave that as just plus c. All right, so normally what I like to do is if I see that there's a natural log, I prefer to solve for c a little later in the process because I know that once I raise both sides base e, this c is going to end up cleaning up a lot of the mess that we have here, or at least get this into an easier form. So, but if I see y squared or y cubed, and if I realize that there's some cube root or something where I have another exponent that's going to impact this side, then I tend to want to solve for c a little earlier. But the natural log tells me, okay, I should be able to get this down to a cleaner form, and I'll wait till this to clean up first, and then I'll solve for c. Okay. Now, ultimately, you can solve for c anytime you want, but just realized, just wanted to share what I think is kind of an easier path for different types of problems. So I'm going to try to get that y solved. So that means I need to get natural log to be moved. So I want to undo natural log. I'll involve base e. E and natural log ends up canceling out. We can begin splitting up that c away from my first e expression here. Times e to the c. Okay, Bailey, do you know what happens with that e to the c there?
C.
Yeah. And we can push that c out in front, drop the absolute value, and let that plus or minus get sucked into that c as well. So I'm going to skip a couple of things here and just jump to this 2y minus 1 is equal to plus or minus c, but I'll just let that c take all that in. Kind of absorb all the plus or minus there. All right, good so far?
Yes, sir.
Okay, so now I just want to solve for y. So just some algebraic step here. I'm going to add 1 to both sides, divide 2. Okay, I'll divide everything by 2. And the good thing is that the c is a constant. C divided by 2 is still just going to be a c value. So we can just let that 2 kind of disappear into the c. All right, so we have our general equation. I typically like to plug information here rather than here. It just feels a little bit cleaner. All right, good so far.
Yes.
Okay, so now we can involve the order pair. The order pair is going to help us solve for the c value, and it'll transform our general to a specific or particular equation. So we'll plug in my order pair that's given to me in the beginning, 0, 1. 0 in for x, 1 in for y, and my goal is to update the c value or solve for the c value so I can update this equation from general to particular. 0 in for x, 1 in for y. E to the 0 is just 1. That's nice. That takes it out. We can just solve for c. Subtract 1/2 from both sides. So c is the other 1/2. So then we're going to update where we started making the substitutions in for x and y. All right, how do you feel about this process?
Feel good.
Good?
Yes.
All right. Next part, find the equation of the tangent line and use it to approximate. So tangent line requires us to find order pair and slope. It says that x equals 0, and the order pair that's given to us earlier is 0, 1. So we need order pair, and we need slope. Obviously, the order pair is already given to us, so we have that. But what can we do to find the slope at that point?
Plug the points into the equation.
Yeah, this is our derivative, our differential equation, which is just a fancy way of saying this is my slope formula. Right. This is basically from first semester we called it f prime, right? But it's no longer f prime because it may not be a function anymore. So it's a derivative formula, but we call it differential equation because it's a derivative equation at the derivative level. Okay, so slope dy dx at 0, 1. Right, so 0 in for x, 1 in for y. Okay. -3 times 1 is -3. So we have our order pair, we have our slope, and now we can do our point slope form for our tangent line. All right. Good so far, Bailey. Good so far, Utsoff.
Yes.
Okay. Now, the second part of D is use the linear equation to approximate f of 0.2. So we want to approximate Any idea how we do that?
Plug 0.2 into the x.
That's right. Yeah, linear approximation, we're using the line to approximate our decimal. So solve for y first. And then we can replace the x with 0.2. I get 0.4. All right, good so far? All right, that's the full number 1 there. All right, number 2. All right. Any idea how to approach this problem? Okay. What do you think, Bailey?
I don't know.
Okay, so initially we're going to ignore the bounds. We're looking at our integral rules and we see nothing that matches up really, right? It's too much for one rule to handle. So that tells us we have to go through what? Okay, U-substitution, right? So what's something that we can do to make it easier to pick out the U value?
Hello, can you hear me?
Yeah, you're back.
Can't you like take out the 3?
We can, but that's not the big picture here. Maybe we can do that down the road, but what can we do to make it easier for us to pick out the U value? Something about that square root.
Make that the U, 1 plus 2EX.
Okay, and rewrite this problem as what? Is there a way to rewrite this problem?
Instead of this root, like the parentheses and then 1/2.
You said parentheses, is that what you said?
Yes.
Yeah, that's right. Yeah, so anytime I'm struggling to find the U value, I'm always going to ask myself, all right, is there a way for me to rewrite this problem? Can I get a parentheses to show up? If I can get a set of parentheses to show up, not always, but it's a good place to at least get something started, right? And usually, again, not 100%, usually that's a good place to start looking for a U value, all right? So if we can target this as our U value, maybe we'll down the road, we're able to get that E to go away and we're able to get this cleaned up to the point where it'll actually match one of these rules that we want to apply. Okay, so we're going to target these two pieces. All right, what's the derivative? What's du dx? What's the derivative of 1 plus 2e to the x? Do you see a rule that we can use?
The first rule?
So what would that look like?
2e to the x times 1?
Yeah. The 1 goes away, right? This one goes away. And also the one that follows goes away too. Now, e to the u times u prime. So e to the x becomes e to the x times 1. All right. Cross multiply here. We want to solve for dx. Divide both sides by 2e to the x. All right, we make our substitutions. Okay, I'm copying everything down, just replacing these two parts here. All right, what happens here? Or does this make sense so far? How we were to make a jump from here to here?
Yes, sir.
Okay, what's next?
Would the e to the x cancel out?
Mm-hmm. Anything else we can do or move or make things easier to approach our next step?
Move 3/2?
Yeah. I'd like to get that out of the way. I know it's part of my answer, but right now I just want to isolate what parts that will be transformed from the antiderivative notation. All right, so what rule do we use for this?
Natural log?
It looks like natural log, but it's not quite it. Do you know why?
The 1/2?
Yeah, that 1/2. We only use this if it's u to the first power in the denominator. It's got to be very specific. So how do we handle u that is not to the first power? Any ideas? Let's have any thoughts?
No, I can't think of any.
Okay. What about this rule? What is this rule? Do you guys recognize this rule?
Yes.
What's this rule called?
Power rule?
Power rule. So what can we do to make it so that we can actually apply power rule?
Bring the u up?
Yeah. So think in terms of this. If it's u to any power, usually it's power rule. But if it's u raised to the first power in the denominator, that's the one case that power rule is going to end up failing. It's going to end up giving us u to the 0/0. So this is more the exception to the rule. The majority is going to fall under the power rule category, which, as we've discovered, is the rule that we use the most often, right? So it's a little bit out of place, but once we bring it up, it's ready to go for power rule. Okay. All right, so what's the result of power rule for this u to the negative 1/2? What does my exponent become?
The CA?
Mm-hmm.
Positive 1/2?
Yeah. And whatever number we have up there, we're going to bring that number below. Go ahead and flip those fractions up to the top. And then bring our our u value back in terms of x. Normally we do plus c, but why do we not do plus c here? When do we know when to have plus c and when not to have plus c?
Is it because we're about to add in the pair?
We're about to add in what?
The 3 and the 0?
Yeah, the bounds, right? So if we don't have the bounds, then we're able to stop at the general solution or a general equation. But we have the bounds, so we know that we're ultimately going to achieve a number, and that number is going to be area related. So we can now work in the bounds. Notice that we need to make sure that we don't stop here. Either we convert the bounds in terms of u, or we bring our antiderivative back in terms of x, so that either way we need to make sure that there's a compatible variable between our antiderivative and our bounds. So right now they're both sitting in terms of x, so we know that we're in the clear to work in those bounds. Okay. Top bound gets evaluated first. Followed by a minus sign, and then lower bound. This is not going to clean up to be a nice whole number. You can leave your answer like this, and that will be fine. Or you can do, I guess you can do a little bit of cleanup here, but if you're able to get to this point, that's good enough. All right, how does that look to you?
Looks good.
Okay. Just be careful with bounds involving 0. I think sometimes students make the assumption that 0 is just going to cancel everything out to be 0. So just be careful here. The 0 is going to make the x 0, but it's not necessarily going to make the entire expression 0. So yeah, just make sure you take the time to plug in 0. And sometimes it does wipe out everything, but not always, like in this case. All right, we have these word problems. Next page. The rise in population of a town is directly proportional to the number present. So all this is going to follow the form of P prime is equal to KP. Direct proportion is always going to be in this form. Everything is in the numerator with this constant proportionality. And then the left side is a change in population, so we call it P prime. And the right side is the number present at any time, so that's just the P value. And then this is always going to transform itself after we separate the variables, after we take the antiderivative. It's always going to convert to be something of y equals CE to the KT. But I'm just letting my dependent variable be population P instead of y. All right, good so far?
Yes, sir.
So really, we're just skipping the calculus here. The calculus is from here to here, but we're just basically using this equation to gather a bunch of order pairs and plug in. We'll be solving for C, then solve for K. Well, will be combination of those things, maybe not in that order, right, we're just using this equation and a bunch of order pairs and just trying to do plug and chug. There's not a whole lot there's no calculus involved here. Right, so let's see if we can gather some information about these order pairs here. They're all going to be in that form of time followed by population. T for time and P for population. All right, so population doubles in 50 years between 1920 and 1970. In 1998, the population was 75,000. What's the population in 1920? So we typically associate C with an initial population. So we know the earliest time that we see is 1920, so we typically like to involve 0 as a whatever starting t-value that we see. So we'll just let 0 represent some population which we don't know, which we'll just call C. That's what C represents, initial value. Population doubles in 50 years. So what order pair can we create out of that?
50 and 2C.
Mm-hmm. And then in 1998, population was 75,500. So we do 1998 minus 1920, and we're going to get 78, right? So we know 78 years after 1920, the population is going to be a specific number now, 75,500. Right, so then we're just kind of taking turns putting this information into the equation, and along the way we're going to hopefully update the equation enough so that we can solve for the C. Right, if I put 0C in, I'm not going to get anywhere. I'm not going to be able to get my C value solved. But the second order pair maybe can help us get to the K value. And then once we're there, the third order pair can maybe help us get to that C value. So I'll plug in that 50 and 2C first. Okay, so I'll insert 50 in for time, T, and I'll insert 2C in for population, P. Notice the C goes away nicely for us, and now we can just focus our attention on this equation. All right, I want to solve for K, but what can I do to allow me to solve for K a little easier? So look at the location of the K variable. Is there any way for us to maybe bring that down? Or what can we involve to allow that exponent to come down?
Natural log.
Yeah, natural log. All right. We know natural log has that nice ability of shifting the location of the exponent so that it makes it easier for us to solve. So 50K comes down in front. Natural log of E is just 1. And now I can just solve for K by dividing both sides by 50. Okay. Update our equation now. We're going to go back to our general equation, replace K with what we found. All right, what do you think we can do next? This is our ultimate goal here. Our goal is to solve for that C. Any ideas?
Plug in the last.
Yeah, I have another T and P value I can plug in, and if I can insert the P and T with numbers, then we should be able to be left with only one variable, and that's the variable we want to solve, right? That initial population. All right. Okay. And the rest is just calculator work. We know that e raised to this ugly number is just going to be a number. We'll take that decimal number, we divide it over, and whatever the result is, it's going to be our C value. So there's our population. Initial population, 1920, it'd be around 25,606. All right, how do we feel about that?
Good.
Okay. All right, let's talk about matching slope fields to the differential equation. So you saw on the first page, we only did a couple of points, right? We're not able to get a full picture, but now all this is filled out, and we know the general solution is kind of going to follow the flow of this graph that we see in front of us, but we're going to be matching, which equation is going to be producing this particular slope field. So what I like to do is I like to organize my information in terms of what I can gather from the slope field. I'm restricted in the sense that I don't know exactly what these slopes are, right? I don't know, maybe that's a slope of -1/2, right? Maybe that's a slope of 1/3. I don't know, right? But what we do know is we know how to get some general information from the slope field. Okay, and I'm going to list out those general things that we are able to tell, even though we can't figure out just by looking at this what the exact slope values are. So the things that we are able to tell, we can figure out where the slope zeros are, right? Those are just going to be horizontal lines. We also know how to pick out slope undefined. Sometimes that just means, do we see any empty spaces, right? If we see empty spaces or empty order pairs, we know those are places where our slope is not defined. We can pick out where positive slopes occur. And we can also pick out where negative slopes occur. All right, so first up, do you see slope zeros on this graph? What's your guess?
Maybe on the X line?
You mean here?
Yes.
Yeah, so that's something, good observation, but something that we got to be careful about, right? Because we don't know what's happening here, right? We don't know, is it a slope zero hiding behind the x-axis? Or is it slope undefined where there's nothing behind the x-axis? Or maybe we're looking at this going, well, maybe that's slope zero sitting here on the y-axis, which could be the case, but maybe it's being duplicated with the segment marks indicating what the y values are. So just to be aware that sometimes we're not able to get a full picture of slope 0 and slope undefined because the axis is not giving us a full picture of what we would like. So if you see slope, if you don't see slope 0 or slope undefined in the 4 quadrants, then a lot of times we may have to leave it as a question mark because we just don't have enough information to make that call. But what we can do is maybe we can gather information about positive and negative slopes. And can you make some general statements about where you see a collection of positive slopes occurring?
Mr. Yang, I'm sorry. I have a DBA right now, and my Fulton virtual teacher is calling me.
Okay. All right. Well, I'll just finish up this problem with Utsav, and then you can watch the recording. Or, but do you think you'll be ready to take it Monday or so?
Yes, sir.
Okay. All right.
Thank you so much.
All right. Good luck. All right. Utsav, can you are you still on? Are you able to have your mic on?
Oh, yes.
Okay.
I think it works. Hello?
So where do you see a collection of positive slopes?
Like on the positive side?
Okay. So wherever the x is positive, right? Whenever x is greater than 0, basically the first and fourth quadrant, right?
Mm-hmm.
All right. And where do you see a collection of negative slopes?
On the y side.
Yeah.
Uh,
More specifically.
2 and 3.
Quadrants 2 and 3, right? So whenever x is less than 0.
Mm-hmm.
So that means that whenever I'm dealing with a positive x value, I should always get a positive slope in return. And if I just have a negative x value, that's enough to cause my entire slopes to all be negative.
Mm-hmm.
So look at these answer choices. Are there any ones that we can maybe eliminate and we know are not going to fulfill these conditions?
B.
Okay. Why?
Because the
Actually,
y
let's see. If we look at B here, you see the y is being squared.
Mm-hmm.
So the y is basically, it has no say as to whether the slope is positive or negative because it's always going to come out positive.
Okay. Yeah.
Right. So when x is positive, this is going to be positive. When y is negative, this is going to be negative. So this is a good candidate, right?
Okay.
All right. So which one can we eliminate that you see?
Wait, are we looking for y negative? Like negative y?
Yeah, we want to look for ones where if x is positive, it's returning us a negative slope so that we can just cross it out.
Oh, okay. Yeah, I see. Can we cross out the letter E?
Okay.
Or is it the same thing as B?
Yeah, I think E is pretty safe as well, right? Same thing as B, where when x is positive, this is always going to be positive. When x is negative, this is still staying negative. So I think B and E are good candidates.
Mm-hmm. A.
Okay. So what happens when x is positive? What's the slope going to return?
A positive.
Positive, that's true, positive x value. But let's say we test a point, right? Let's say we test 1, 1. We know 1, 1 is going to return us a positive value, right?
Mm-hmm.
What happens when I plug 1, 1 in here?
The y equals negative.
Mm-hmm. What's my overall fraction going to be?
Negative.
Negative, right? So negative, even when x is positive, I'm getting a negative value. So that tells me, all right, it's not consistent with what I know to be true. So this can't be true, right? Even if I find one case that it fails, that's enough for me to eliminate it.
Yeah.
Okay. Anything else?
X squared, no.
Okay, what do you notice about this one here? What do you notice about x squared, y squared, x squared over y squared?
They're both gonna be positive.
Yeah, so no matter what, this is positive, right?
Yeah.
But we know that we do see some negative slopes, so that's not true with what because if it's truly positive slope, everything here should be positive.
Mm-hmm.
But we see a bunch of negatives, which can't be true if this is, so we know this is out.
Can we cancel D out too?
Yeah, D, if I plug 1, 1, I do get positive, but if I choose a different order pair here, if I choose, or I mean, let's choose this one here, 1, negative 1. If I plug 1, negative 1 in, I should get a positive number. But if I put 1, negative 1 in here, I'm getting negative, and that's not consistent. So we're down to B and E. Any ideas how we can decide between these two?
B is gonna be positive, right?
Yeah, B is good in terms of the positive and negatives. They're good, but the only difference is that the y squared is above and others below. Maybe we can test the extremities here. Let's test something that is, on the outer edges, right? Let's say we tested 10, 10.
Mm-hmm.
If I plug 10, 10 into both equations, is one going to be obviously incorrect?
Yeah.
Which one?
E.
Why?
Because the y equals 100 over x, and that, wait. I don't get it. What do you mean? Like,
Right, so tell me what happens if I put 10, 10 into this equation.
the x equals 10,
Okay.
and then the y squared equals 100.
Mm-hmm. So
10 over 100.
yeah, what does that look like? What does 10 over 100 look like? Or what does that reduce to be? 10 over 100.
1 over 10.
Okay. What do you know about 1 over 10 in terms of slope?
Oh, it goes right 1 and up 10.
Okay.
Or is that opposite?
Yeah, that's right. That's right. It goes up 1 and over 10. So what does that tell you about the slope? Or what does that slope look like?
It's not really steep.
Yeah. So I think that is consistent with this one, right? What
Yeah.
happens if I put 10, 10 in here?
100 over 10, so
Right.
10 over 1.
Right. And that doesn't look like a slope 10, right?
Yeah.
So sometimes we may have to kind of go to
I
specific
see.
order pairs to kind of help decide, all right, which one of these is going to be the one that we can eliminate. And if I test a point, obviously, we don't know what this exact slope is, but we can tell the difference between, 100 versus 1/10, right? And so we're using those distinctions to kind of help narrow down our choices, even though we don't know by looking at this what this exact slope is, but we have some idea, right? So E is out, just B.
I see. Yeah.
Okay, 5 is just U-substitution, identifying the integral rules, and then picking out the U value and flipping it. 6 is arc-trig, 7 is also arc-trig because of the difference in terms of the degrees, and the bottom is much higher than the numerator. So we know those are good candidates for arc-trig. This is going to be synthetic division, and this is going to be U-substitution with natural log of x being the U value. Okay, we can do one more. Which one? Is there one that stands out that you want to see done?
The last one, the 9.
Number 9. Okay. Yeah. So that 3 is kind of throwing us off. It's kind of makes it more complex. But we have a property, power property, which allows the exponent to freely come down. So we can do that without changing the overall value. So I'm going to bring that 3 down and make things easier for us to work with. Right. Exponents for natural log are free to move. So I'm going to first bring that 3 down. once that 3 comes down, we can multiply the 2 and 3 to be 6. We can push the 5 out, makes it a little cleaner for us to look at. And then we're left with a 1 over x ln of x dx. Now, it becomes a lot more clear, a lot cleaner. We want the u value to be a significant portion of the problem. X ln x is a little too much, so we're just going to target the natural log of x to be our u value. And we're hoping that this x will just go away on its own when we go through U-substitution. Okay, so here's our u value. Oops. We know the rule for natural log of u is u prime over u, so natural log of x just becomes 1 over x. Cross multiply. Make our substitutions, so u can replace natural log of x, and then x du can replace the dx. We should be able to get that x to go away. Right, we see that clean relationship here. X just goes away.
Oh, you multiplied it. Okay, I see.
And now, what does this look like?
The one below natural log.
One below natural log? I
Oh,
think this is natural log, right? Isn't this matching with this one here?
but didn't we already use natural log in the first part?
That was just the u value, though. That was just to get up to this point. Our u value to du is always going to be on the derivative side of things. And then once we get to this part, we're trying to match with one of these integral rules.
Oh,
So that matches with our integral rule, right?
yeah.
So natural log absolute value of u with the 5/6 hanging out in front. And our final step is what?
To eliminate the power, the absolute value.
No, we keep the absolute value. But how do we represent our answer? We basically have the answer. Just have one little thing to do.
Put in the first part.
Yeah, what do you mean by that?
Like the 1 over natural log of x.
We're basically at the answer, but there's something we can do with this.
Oh, you just turn it into not.
Yeah.
Don't you just substitute?
Yeah, that's it. Yeah, so just that last step, right? We started with x. We went through U-substitution to help us through the process, but now that's just a temporary variable. We're going to bring it back in terms of the original variable.
Okay.
All right. You want to try taking that again on Monday?
Monday? Yeah.
Okay. And then you want to do after school?
After school, yeah.
Okay. All right. So I encourage you to work through the rest of these problems, look at the key, and hopefully you can match the rules. Then you can go through U-substitution for these two, and then go through synthetic division for this one.
Yeah. Wait, the The 8th one is synthetic, right?
Yeah, synthetic. Yeah, and then this is arctangent, and this is going to be arcsecant.
Okay.
All right. Hope you have a good weekend. I'll see you on Monday.
Take care.
All right. Take care.